Hello everybody, my name is Timo Roine and I will present today the Connect to Brain project. In this project we will develop a multi-locus transcranial magnetic stimulation device capable of connecting to the networks of the human brain. This project is a ERC synergy project of Aalto University Finland, University of Chieti-Pescara Italy and University of Tübingen Germany. And its duration is from 2019 until 2025. Transcranial magnetic stimulation activates the brain non-invasively through electromagnetic induction. It is used for pre-surgical motor and language mapping and for treatment of neurological and psychiatric disorders, for instance depression. However, the current technology has several limitations. It can be only used to stimulate a single location, and changing the locus of the stimulation is very slow and operator dependent. It is also blind to ongoing brain activity. These limitations might lead to relatively low therapeutic efficacy of the current treatment protocols. To address these limitations, in this project we will improve the state-of-the-art brain stimulation protocols by developing multi-locus TMS devices able to electronically change the locus, direction, intensity and timing of the stimulation in real time. In addition, we propose to take into account ongoing brain activity measured by EEG to determine when and where to stimulate the brain next. This form of stimulation is called closed-loop stimulation, and we expect that it will result in much lower variability and a much larger effect size. To reach the goal of Connect to Brain project, we will need multi-locus TMS, real-time closed-loop system, and algorithms for the characterization of brain state, activity and connectivity. But most importantly, we need to translate these methods into clinical practice. In this video, we show an illustration of the proposed technology. The stimulus can be moved fast and reliably without mechanical coil movement. In addition, multiple spots can be activated, also simultaneously. EEG and other signals are measured to allow computer algorithm to design and perform a sequence of simulations in closed loop. The project is divided into 3 parts, all of which work together towards the final goal, which is multi-locus TMS therapy. The 3 parts are all closely linked together. For instance, we need neurophysiological models to know what kind of brain state we need to reach to be able to develop this kind of algorithm and therapy. But we also need algorithms capable of estimating the brain state in real time to inform these neurophysiological models. In the closed loop, we start from high-density EEG data, from which we estimate brain source activities with inverse method. Then we estimate connectivity metrics, for instance by phase-based metrics, and we can use prior information from MEG and MRI for both of these steps. The time required for this part of the loop will be crucial. The parameters and brain states need to be estimated to be used in a machine learning framework which will define the next stimulation parameters for the multi-locus TMS device. In summary, the closed-loop system should be able to measure and predict the brain connectivity and state, and control the brain towards a desired state using real-time artificial intelligence methods. In the development of the multi-locus technology, our approach is to increase the number of TMS transducers by placing them over each other in several layers instead of side by side. This way, each coil produces a basis function for the electric field. By combining these basis functions or components, we can move the locus of the stimulation millimeter by millimeter and also change the direction of the induced electric field. The first prototype will consist of 5 coils and is capable of moving the locus of stimulation within an area of 3 by 3 centimeters and changing the direction of the field. However, the final prototype might contain up to 50 coils to be able to stimulate almost anywhere on the cortical surface. In addition, we have developed real-time tractography-based neuronavigation, which can estimate the structural connectivity of the stimulation site in real time. This can be used for the neuronavigation in this system. This method is presented in more detail in the poster presented by Dr. Eidogan tomorrow. The ability of the multi-locus TMS system to electronically control the stimulation location and orientation will also allow, for instance, automatic algorithms for the target search. These provide an operator-independent way to find, for example, the motor hotspot. On the right, there's an example of the stimulations performed by the algorithm in order to find the optimal site, marked by the X. The Tübingen group has demonstrated the feasibility of closed-loop TMS by analyzing EEG in real time and accurately predicting the occurrence of a specific brain state. In this case, the next peak or trough of the mu rhythm over the sensory motor cortex. These conditions represent states of low and high excitability measured by the motor evoked potential signs. Stimulating repetitively the same brain state results in long-term depression or potentiation-like plasticity. This finding is very important for our project. The same stimulation protocol leads to opposite change in the brain. So the outcome critically depends on what brain state the stimulation was performed in. And it is the brain state primarily that affects the outcome. In addition, the Tübingen group has shown that the phase synchronicity of the conditioning stimulus and test stimulus in the motor cortex plays a role regarding the intracortical inhibition. These 4 conditions occur very often in the brain, and thus the real-time system is able to wait for the optimal conditions to occur. And this specific experiment showed that the inhibition is stronger for the in-sync condition. In summary, the Connect-to-Brain device will be a revolutionary instrument capable of stimulating the brain in completely new ways. It will be a game changer in treating brain disorders by improving the therapeutic efficacy. It will also provide novel insight into human brain functions. And if the translation to clinical use is successful, it will also massively reduce public health costs. Finally, this is a group photo of most of the personnel working in the project from Aalto University, University of Chieti-Pescara, and University of Tübingen. Thank you for listening.